Hello, my name is Miranda, and my group members are Rhianne and Zach. So this is our project one for the term, and we chose the turntable for our problem. So here's our problem. We're told that a box is on the edge of a turntable, and it's turning at a constant angular speed. Now a string is attached to that box and passes through a pulley and goes through the middle of the turntable and is then attached and wrapped around a ball. It's wrapped around a ball, it's not attached, to a hollow ball hanging off that turntable. And we are supposed to find the angular velocity of the turntable system. So here's our knowns and unknowns. We're given that the mass of the ball is equal to big M and the mass of the box is equal to little m. And then the radius of the turntable is equal to big R and the radius of the ball is equal to little r. So our assumptions is that the turntable surface is frictionless, and so is the spinning of the turntable is also frictionless. And we have the ideal string that has constant tension throughout it. And then the pulley is also massless, so there's no force of the pulley acting on that string. And the ball is being pulled from the edge of it, so its rotation center is going to be the center of the ball. And the ball is also hollow. And so our unknowns are, of course, the angular velocity of the turntable, which we are trying to find, and we need to know also the force of tension in the string and the acceleration, but it's going to be the centripetal acceleration of the box. And so here's our free body diagrams that we drew. This is the box. We have the normal force from the table acting up on the box, and of course gravity. And then we have the tension from the string going to the right. And then we have for the ball, we have it turning, and then we have the tension from the string acting on the edge of it, and of course gravity acting on the center of mass of the ball. So here's our equations. We are using angular momentum, and these can be our equations and also concepts that we are using throughout this problem. We have angular momentum, and we have kinetic angular energy. And then we also have translational momentum as well. And then we are using net torque and acceleration, centripetal acceleration, and the force of tension equation as well. All right, that is the end of our intro for this problem. Thank you.
Okay, to start to solve this problem, we're going to start with the equation torque is equal to inertia multiplied by alpha, which is angular acceleration. Now, torque is net torque. In this situation, the only torque acting in the system is due to the ball. Specifically, the rope pulling from the edge of the ball while gravity pulls from the center of mass. That creates this, force vector, which is equal to the radius, and then we can find the torque. So, net torque in this situation is the force of tension multiplied by r, the radius, which is our position vector, set equal to the inertia of a over r. Because we want to get rid of this r over here, we're going to convert this angular acceleration to translational acceleration, which the relationship between those is angular acceleration is equal to translational acceleration over r. We can rewrite this as f of t is equal to I a over r squared. Now, we can solve for f of t in terms of A in our general force equation, which will always be, due to Newton's laws, F equals ma. So we're going to put that equation up there at the top to keep for later. And now we're going to go plug this into our force equation. Now, we have a couple of different forces acting on this system, the total of which is going to equal mass times acceleration. That's going to equal m2g. m2 is the weight of the ball multiplied by gravity minus the force of tension. Now, we have found the force of tension in terms of inertia, acceleration, and the radius. So we can plug that in. I is equal to a over r squared. And from there, we're going to solve for a, because we need to get acceleration out of this equation. So I'm not going to show all the algebra, because again, that's long, but we end up with acceleration is equal to 3/5 times gravity. Okay, that is our acceleration of our system. Now, the reason we only have these two forces acting in the system, because these are the only two forces here that don't cancel out, gravity on the ball and force tension. Okay, so we have our acceleration. Just like we did our other equations, we're going to pop that up here to save for later. And now that we have our acceleration, we can solve for our force tension. Now, remember our relationship up here. We can then use that relationship to solve for force tension, because now we know acceleration. So we just sub in acceleration into this equation up here. So that gives us F of t, force tension, is equal to moment of inertia multiplied by 3/5 gravity over r squared. And again, we also know the moment of inertia because this is a hollow ball. So that gets us 2/3 mass of the ball, r squared, over 3/5 gravity over r squared, equal to force tension. Yay! Now, solve this out, cancel things out. Not going to show the whole process because, again, unnecessary, but we're going to get force tension is equal to 2/5 mass of the ball times gravity. Okay, now we have another little equation that we can come up here and secret away. Okay, now we have a force tension. And if you remember, we have force is equal to ma. Now, because force tension is equal on both sides, we know that the force tension of the block, mass 1 is referring to the block, times acceleration is equal to Ft, force tension. Because the force tension is directly acting against your acceleration due to the turntable spinning. Now, we can rewrite this as the mass of the block multiplied by the radius of the turntable, angular acceleration squared, equal to the force tension equation we just found. Great. Now, we have the variable that we're looking for. Now we want to solve for W. Again, I'm not going to show the whole math because it's long and complicated. It's not very long, it's not very complicated, I just don't want to show it. But that leaves us with omega is equal to the square root of 2 mass of the ball times gravity over 5 mass of the block times the radius of the turntable. Now, the reason we set this force tension equal to the mass of the box times the acceleration is because the mass of the box is the only one that is experiencing this angular acceleration. The ball is not. The ball is not experiencing angular acceleration. It's through the middle. It is rotating, yes, but it's not experiencing the angular acceleration of the turntable. So we needed to solve for tension using the ball, because we had enough information to do that, and then set it equal to the box, because this is an ideal pulley and the force tension is equal on both sides. So that just gets us this nice little equation right here. And then Zach's going to take it away with sense-making.
Now that we found out our equation, it's time for the sense-making. So the first part of the sense-making I wanted to do was to check our units. So the units for omega are rads over seconds. But rads are dimensionless, so you can think of that as 1 over seconds. So when we plug in our equation and we separate each part by its component and give its units, we have the square root of m times m over seconds squared divided by m times m. Once we run through the math, we find that this equates to 1 over s, so our units match. So the first part of our sense making means, so far, the equation makes sense. After that, we are going to, I ran 3 tests, 3 different hypotheticals. The first one I ran, I set mass 1 to be twice the weight of mass 2. And that came out to be 0.577 rads per second. I ran test 2, where I had mass 1 and mass 2 to be equal. And that came out to be 0.816 rads per second. And for test 3, I had mass 1 be half the mass of mass 2. And that came out to be 1.15 rads per second. And I have the RPMs here, so 5.5, 7.8, and 11 RPMs. I visualize these RPMs here. So for the first test, this of course isn't a turntable, nor does it have like a mass on it, but this is just meant to visualize the speed that it would be rotating at if you just want to imagine a mass sitting on the edge of this. So this is for the first test. The second test, where the masses are equal, and the third test, where mass 1 is half the mass of mass 2. Alright, so for the reflection, I found that this project assignment actually had a lot of similarities with activity 2 on homework 4. Mostly because you essentially use the same equations that you would there, use the same here, and the whole point of this question was to find angular speed, and that's kind of what we were doing here.